the material properties. So this is up to this point, and not the full curves here, only the partial curves up to this point was used in the pushover analysis. Okay, but in dynamic analysis now you have to specify the ground motions also, right? You have to specify the section properties in a different manner. You have to specify the material properties in a different manner. So the type of input quantities required here is huge. And then what are the types of output? So you can plot the acceleration, the velocity, the displacements at different levels. Then you can convert it into the peak story drifts. You can convert them into various outputs at different levels. Now let us see how do we model it? How do we consider the non-linearity? So this similar model. Now the additional parameter that is required here is the damping. That was not required in the pushover analysis. So we can consider the damping. For example, the Rayleigh damping we can use here. Now the most important point here is the modeling of the reinforced concrete element. Now in dynamic analysis, you have to be careful which type of modeling you are doing. So here it is always beneficial to use the fiber modeling. So fiber modeling means you divide the member into different fibers along the length of the member. So if you see here, this is the RC element section. This is the unconfined concrete fibers, right, outside the stirrups. And these are the confined concrete fibers inside the stirrups. And these are the steel fibers. Okay, so this is RC element section is a combination of these three. Now these are specified along the length of the member. So here you can see that this is the length and these are the slices which are the fibers actually. So these are specified in that manner. And for each of these fibers, you have to specify the material properties. Now these material properties cannot be simply like moment rotation curves for the pushover analysis, because the dynamic loads now are cyclic in nature. Okay, so you have to specify to software how this member, how this section is going to behave in a cyclic manner, not monotonic but no cyclic. So you have to specify the degradation behavior also. So let us see how it is done. So for concrete, now let us look at here how you need to provide the input properties. So this is moment and rotation. So initially you will have increase and then some strain hardening. Let us say when the material reaches this point, the change of direction occurs. So the earthquake shaking changes the direction. So as soon as it changes the direction, the material has to degrade, come back. So you have to specify how the material degrades. And then when it was degrading, then again the direction was changed, let us say. So then again it will increase, right? So this is not simple thing. This has to be specified in a very complex manner, and there are methods available. So Takeda et al., let us assume that we can consider. There are various models available. So Takeda et al. Is one of them to model the proper material response in a non-linear degradation manner. So this Han et al. Model is used for your reinforcement. This model proposed by Cavalieri and Trapani in 2014 can be used to model the cyclic degradation behavior of masonry. So now you can see here what happens. This is the no tension branch, right? So this is the compression. Okay. Now masonry is good only in compression, even though it wants to undergo that cyclic behavior, but we know that the tensile behavior is very poor. So how to model them? Reinforced concrete of course has good tension and compression properties, so we can do this. So in case of masonry, there is a pivot model. So what we do, we consider a point here which is called the pivot point, and all these values are changed about this point. You can see. So this is a pivot. So this is the stress strain curve or the load deformation curve in compression. So this is strength envelope. But during earthquake shaking, if from here it has to degrade, then you have to specify how it can go back, what is the slope, then how it reaches here or it goes back here, but this is tension. So it has to go back from here and then again increase in strength, come here. So this is the way you have to specify. So there are various branches, 1, 2, 3, which were proposed by these authors, and normally people use this. So once you specify these material properties in a much complex manner, which are not easily available in the literature, the next step is to specify the ground motions. Now the question will be, which ground motion should you use? There are thousands of ground motions available in literature. So there is in fact a code, not in India, but in some other countries, there is a code for selection of ground motion. Right? So it says you that you do this. So people say that if you consider 50 different types of ground motions, only you can be comfortable that your structure will be safe if you design for those design forces. So here I am showing you some of the parameters of different ground motions that you have to consider when you choose them. So this is for 3 ground motions, 1940 El Centro, 1943 Indo-Burma and 1985 Chile. So these are the 3 ground motions that I have considered. So the P ground acceleration is one important parameter, magnitude is second, bandwidth is third important parameter. See the change in the values here. The dominant frequency, the ground motions that you consider should have different dominating frequencies. Central frequency is another definition. Area's intensity is another definition. Strong motion duration, you can see the change. So all these studies, they say that you have to consider these ground motions with different parameters. So that, see, now what is happening here, the basic fundamentals are changed. In linear static analysis, the structural behavior is not a function of type of loading, right? So you apply whatever loading, the behavior you know. But the nonlinear dynamic analysis or even the nonlinear static analysis, the structural behavior is a function of the loads, how you apply the load. So for different ground motions, you will have entirely different output of the structure. So that is the whole problem. So you have to be very careful when you choose these ground motions. So the output here, the energy density curves for these 3 different ground motions are shown here, using which you can compute the properties. Sometimes people develop their own synthetic ground motions. Like somebody was asking how to change any given ground motion to a synthetic ground motion such that the response spectrum developed for the synthetic ground motion becomes similar to the design response spectrum of bias variant time. So that is perfectly possible. You can actually uh, uh, develop your own ground motions, the synthetic ground motions, such that the structural response will be critical. So that is, there are methods available for that. So now, once you do that, you have these kinds of outputs. So the nonlinear dynamic response will be, you can plot the joint displacement. Every joint displacement you can plot with the time. So this is the output time history for the joint displacement. So the maximum displacement was 0.2 meters at time of, let us say, 28 seconds. That you can specify from here. Base shear also you can plot with respect to time. Here I'm showing you the peak interstory drifts. So what I have done here, for every story, I have plotted the joint displacements and tried to see for every story which joint has the maximum displacement. So I'm considering that and plotting here. So this is for one story. For second story, what is the maximum displacement into the entire joints in that story, third story and fourth story. So this is what is shown here. And on the x-axis is the peak ground acceleration. Right? No, I'm sorry. The x-axis is the interstory drift. So how much is the drift? And these are the story levels. So obviously, when you increase the peak ground acceleration, you will have increased deformation. So you will have increased interstory drift. But it may happen that the story drift at a particular story may be lesser or more than the adjacent story. That is perfectly possible because it depends on the mode shapes, it depends on the mass distribution. So this is for the bare frame where there are no impels. So in both positive and negative directions are shown here. So this is positive and this is negative, both are shown here. You can also do similar analysis for open ground story. So now I just wanted to highlight here, that is why I am showing you these two results. For open ground story, 5-story frame, you see where is the displacement. The displacement is only in the first story. The upper story displacements are almost zero. So this is even applicable in case of nonlinear dynamic analysis. You can convert these responses to the cyclic response. Like we did considering the ADRS curve, you have to actually plot the acceleration quantity on the y-axis and the displacement quantity or the displacement quantity on the x-axis. That is possible. You can do this, and then you can compare your results with the experimental results also. The next stage of carrying out the nonlinear dynamic analysis is plotting the IDA curve. So this IDA is the incremental dynamic analysis. So meaning we have to consider large number of ground motions with increasing order of magnitude or PGA. So every point here is the output of one dynamic analysis. Right? So this is the output coming from one analysis, this is the output of another analysis. So you carry out several analyses and then you can act for the same structure. So, and you carry out, no, I'm sorry, this is the single record. This is a single record time history analysis. For a different instances, this we are showing here the maximum interstory drift. Sorry, that is here actually. What I was saying is here, but this is for single record. You keep on increasing the severity, and we get here is the collapse. So what is shown here is the collapse for the single scale nonlinear time history analysis. Now, how do we define collapse here? So there is a literature available, many papers which say that if the slope of this line is less than, let us say 25% of the initial slope or 30% or 20% of the initial slope, then you can say that it has collapsed, right? So here it is the spectral acceleration that you have plotted. You can also plot the peak ground acceleration for the single record. So it means that you have considered one record, but you're changing the peak ground acceleration or you're changing the spectral acceleration. So some intensity measure you are changing for the single record and you're plotting this for the same structure. Now you can also do this for multiple records. So here you can plot, you can consider thousands of ground motions, hundreds of ground motions with different values of PGA, with different spectral acceleration, and do the same incremental dynamic analysis and try to plot these results. So then you can see which are the ground motions for which the structure failed and at what level. So this will go on increasing. I mean, whatever you want to do, the opportunities are endless. You have so many of opportunities.
Sir?
Yes.
Sir, is there any option in SAP 2000 to get the output in terms of base shear, story shear directly?
You can get the base shear and story shear, yes. I mean, story shear, no, but base shear you can get directly.
Sir, in graph or in values?
No, in graph. See, when you plot this capacity curve, it gives you the base shear versus drift level versus lateral drift. So that is the total base shear of the system. And if you want to do it, if you want to compute the story shear, let us say, then you have to look at the output file, where for a particular level of at a particular floor level, you have to find out what is the shear in all the columns. So from there you can get the story shear.
Okay, thank you.
Yeah. So finally the checks. Like I showed, the capacity should always be greater than demand. It has to be under reinforced design, stresses less than the design limits, deformation less than the design limits, columns stronger than beams. If these criteria are not fulfilled, redesign. Now I will ask you, which method will you use? The nonlinear dynamic analysis, which is so complex, which requires so many things, and which requires a lot of post processing for a simple structure, or you will use some method in which on which you have more confidence, which are easier to understand and on which you have more confidence. So that is why I'm saying you check the computer results with simplified methods always. Whatever type of analysis you do, always check your results with the simplified methods. But there are some structures for which the simplified methods will not be applicable entirely, not at all. But still, it will give you some results, maybe 100% error, maybe the bending moments will be double or half than what it should have been. But it will not be 100 times more, and it will not be 10 times more. Believe me, I have cases where students come to me with natural period of 1000 seconds, right? So they do some analysis, they become happy about it, that SAP has given me results, and then they show me the results, nice curves, pushover curves. But then when I ask them what is the modal where is the modal property? Checking the modal property, I get that is a 50-second time period, 100-second time period. So these are the common mistakes that we do. So we have to be very careful when you do, especially this nonlinear analysis. So thank you very much. If you have any questions, we can address. I hope I was not boring today because it was hugely theoretical.
Not at all, sir. Thank you, sir. I would like, if participants have any question, they may ask.
Hello.
Yes.
So generally in the numerical analysis, the model can run for as long as we want. For example, if I give 120 mm displacement, the model will run for that also. But in the realistic experiments, that model will be damaged even before that. So how
You're
can we?
not audible. You're not audible fully.
Hello.
Yeah, I can hear your voice, but some points I could not hear. Just repeat.
Okay, sir. So in the numerical analysis, the model can run for as long as we decide. For example, we can give a 120 mm displacement, so the model will run for that also. But in the experimental analysis, the model will get damaged even before that. So how can we decide a point for numerical analysis that this simulation should run only up to that?
You are talking about the pushover analysis.
Yes.
See, in pushover analysis, there is no problem because if you are doing the analysis in SAP 2000 or STAT, so these softwares which have closed form solutions for frame elements, let us say, then there is no problem. You can go on increasing the displacement until the structure fails. So at one point of time, the structure will fail. You will see the capacity curve reducing. But if you are doing this type of analysis in some software in which this degradation is not possible, for example, if you model these structures in Abacus or let us say Snap 2 DX, or there are some other simple softwares which do not
ANSYS
consider
also
this
I've done.
degradation. Huh?
In ANSYS also I've done ANSYS.
Yeah, in ANSYS also. So there, this thing is not possible that you cannot drop that capacity. So in that case, you have to actually decide a drift level up to which you are interested in determining the design forces. So one such drift level may be the design drift level given in the code, which is very less, or you may say that experimentally I found that up to 1% drift, the structure was performing really well. So let us see what happens in ANSYS at 1% drift. So that you have to define. But in software like SAP, you can very easily see the entire capacity curve till failure, till it drops to almost zero. That is possible.
So since we are considering many factors of safety in our design process, so should we also include that in the analysis during the drift calculations?
Not at all.
Management.
Not at all. That is what I told you, that if you are doing the nonlinear analysis and you're trying to find out the real response of the structure, not the design response. See, real response will be completely different because when you test, let us say, a frame or simple concrete cube in lab, what you get is not FCK. What you get is the target strength, right? You are designing those cubes for a target strength. What is FCK? FCK is not even the average value. If you remember that Gaussian, the distribution, FCK lies here after this 95%. Okay, so just 95% of the value should be actually be more than that. So we are here, not even in the average level. So what I'm saying, in the realistic material strength evaluation, you forget about all factors of safeties. Otherwise, what you get is the design strength, not the real strength.
So, for example, if I have to consider M25 concrete in a column section, so
Yes.
the properties should be M25, or should I reduce it?
No, you increase it. How can you reduce it?
Because
See,
in the
I'll ask you one question. If you have this M25 grade concrete, what strength do you expect in lab? You prepare M25 grade concrete in lab, prepare those cubes, try to fail those cubes in CTM. Do you expect lesser strength than 25 MPa or higher strength?
higher strength in there.
Higher strength, obviously, because if it is lesser, then your design is failed, right? You have to design for FCK 25. Now, what is the target? Target is this FCK plus 1.65 sigma, right? If you remember
Yes.
that equation. So
Yes.
that is the value you expect. So for 25, if I remember correctly, it comes out to be around 32, 33 MPa.
Yes.
Okay, so that value you have to consider.
Even for
Only
steel.
then, sorry,
Even for steel.
steel also. So if you go to lab and test this bar in tension, what is the value you get for Fe415 grade steel is about 440, 450, 430, 480 MPa depending on the manufacturer. If you are testing good Tata steel, then you will get up to about 470, 460 very easily, 480. Right? So that
So,
is the real strength. But then in design, what we use is 0.87 Fy, even lesser than Fy.
so we should use the ultimate strength in the analysis.
Yes.
Okay, sir. Thank you.
See, if you are interested in finding out the realistic behavior of the structure, then you have to use the realistic material properties. Okay, if you are trying to replicate the experimental study numerically, then obviously you have to consider the realistic strength.
But sir, if we will consider a higher strength, the modulus of elasticity will also increase.
See, that is the thing that I informed you, I think, first or second lecture. This E of modulus of elasticity of concrete, 5000 root FCK.
Yes.
It is also an average number, right? It is there because there has to be some standardization. Okay, otherwise, if anybody will use anything, then there is a problem. So, if you can determine E experimentally, then you will understand how much is the error in your model. But most of the people, they don't obtain this value experimentally. Second point is, even if you obtain that value experimentally, the amount of cracking, the amount of reduction will be different than what is specified in the code of 70% to 30%. So best way is not to worry about E value in nonlinear analysis. You just specify whatever you know. So 5000 root FCK for steel and 2 into 10 to the power 5 MPa for concrete and 2 into 10 to the power 5 MPa for steel. And then you see how to match your results during that stage after you get. So you go on reducing that E value of concrete. That is the way generally we carry out.
Okay. So we should consider a higher strength and then calibrate the model for the modulus of elasticity.
Yes.
Okay, sir. Thank you.
I will
Sir,
not say real strength, I will say real strength.
Okay. Yes, I got it. Okay, sir.
sir, sir, in slide number 14,
Hmm.
hello, sir.
Slide 14, what happened?
Sir, in slide number 14, where you showed the location of plastic hinges and the expression proposed by Paul and Priestley,
Hmm.
sir, in basic structure analysis, we define the location of plastic hinges in the location where there is the maximum bending moment. In the
Yes.
location of maximum bending moment. But sir, in that particular slide, why the plastic hinges are shifted a bit? I mean, like if it's a single bay frame with fixed bases, there has to be 4 plastic hinges, 2 at joints and 2 at the supports. But so in that particular slide, the plastic hinges at the joints are a bit shifted. So why is such?
Let me show you that slide again.
So slide number 14, sir.
Yes. Can you see?
Yes, sir.
Okay. See, this beam column joint is rigid. Okay.
Yes, sir.
Now, when the beam column joint is rigid, we generally do not expect that it will damage during the real earthquakes or during the testing also. And that is what we have also seen in that video of that single frame testing. So it has been observed that the most of the damage will not occur right at the joint, but at a distance of LP/2 from the face of the joint. So that is why these are shifted. Now, LP is the length of the plastic hinge. That means this is the zone where you have the maximum damage. Now, LP starts from the face of the column or face of the beam along the length of that member. Right? So, for example, from this point to this point is the LP. So, this is the region in which maximum damage will occur. So, what we consider where we assume this plastic hinge is at the center of that LP. Okay.
So at that location, the bending moment is not critical. So at that particular location,
The bending moment is, bending moment is not alone important here, but rotation is also important. If you remember, let me see if I have, yeah. See, what is the rotation right above this joint? There is no rotation. The rotation actually starts slightly above that. Because
yes,
of
sir.
that fixity, you see, the maximum bending moment, though it appears here, but it is so rigid that we don't have to worry about it here. We can consider slightly above that. And how much is that slightly is governed by this equation.
Okay, sir, I've got it. Thank you, sir.
Yeah. And more importantly, you see, here I am not considering the dead load. If I add dead load here, you see the zero bending moment will not occur at the center of the beam.
Yes, sir.
It will be shifted. And similarly, these will also be shifted when we combine the axial load versus the lateral load. Okay.
Okay, sir. Okay, sir. Thank you.
Hello, sir.
Yes.
Sir, how can we model plastic hinges in shear wall? As you say that we have to model it in layers.
See, the what I was saying is the method given in the SAT 2000. See, SAT 2000 has this capability of modeling nonlinearity in shear walls in a layered shell element. So, if you know what is a shear wall, so it has concrete. So let us say this layer is the outer layer of concrete. This layer is the inside layer of concrete. This is the room. So this is inside layer of concrete. This is external layer of concrete. Then you have a layer of reinforcement, and then you again have a layer of another reinforcement. So I am assuming that the bars are there in two directions. It may also happen that these two layers of reinforcement are there on this face, and another two layers of reinforcement are there on this face. So on both the faces you have reinforcement. Right. Now the capability of SAP is, it says that this outermost layer of concrete you can model separately. Then you model another layer of steel, connect these two layers, then another layer of steel, then another layer of concrete, then a layer of steel, another layer of steel, and a layer of concrete. So for these individual layers, you specify the nonlinear properties. So concrete or steel, you specify them, and then somehow it integrates and then do the analysis. Now the problem here is you cannot define the hinge. So the nonlinearity is distributed on the entire shell element. There is no hinge. So what you get as output is not the failure of the hinge, but you get the stresses. You get the stress, you get the strain of this on different surfaces of these elements.
Sir, is it same for both slender or the squat walls?
Yes, for any shear walls you can do that.
Thank you.
Hello.
Yes.
Yes. Yes, sir. Sir, during the analysis of masonry infill wall, is we consider the weight of strut because we already consider the weight of wall.
No, if you have already considered the weight of the wall, you don't have to again consider the weight of the strut. It's not required.
Okay, sir. Okay,
But
sir.
I will rather say that
And so second,
you should never consider the weight of the strut, because the dimensions of the strut are different than the dimensions
yes,
of the
sir.
wall, right? So you always transfer,
Yes.
or you always consider the weight of the wall on the beam, and then you model the strut, which should be
Okay,
weightless.
sir. Okay, okay. Oh, got it, sir.
Sir, can we model the gravity, concrete gravity dam in the SAP 2000?
Sorry, I couldn't hear you. What?
Sir, can we model the concrete gravity dam in the SAP 2000 for
Yes,
non-linear analysis?
for non-linear analysis.
Yeah.
I'm not sure. I don't think you can do that in SAP 2000, because when you say concrete gravity dams, I assume that you are asking me about the solid elements, right? Not the frame elements or the shell elements. So in SAP 2000, you can consider the non-linearity in the frame elements and the shell elements, not in the solid elements. So, but then you can carry out an analysis in SAP 2000 considering these solid elements, and try to see what is the variation in the stresses, what is the variation in the strains, and then depending on the material, you know what is this failure strain of concrete, what is the failure strength of concrete. So from there, indirectly, you can check the safety.
Yes.
But
Yeah, we,
for real analysis, we have to use some pilot element software.
abacus,
Yes,
abacus,
yes.
abacus is more better than SAP 2000.
No, you see, when we say better, the problem is, if see whatever I have shown you today is the nonlinear dynamic analysis for frame elements only. Now, when you include the solid elements, their behavior, their interaction with other elements, at every node you have to specify the interaction. You have to specify how the different solid elements they interact with each other, right? What is the failure mode? How you want to define the failures? The input required is huge. Though we say that it can be done in a better, but it is extremely complex. It is not easy.
Yes. Okay. Thank you, sir.
Yeah.
Hello.
Hello, sir.
Yes.
Hello, sir.
Yes.
Sir, I have studied that time history analysis is more preferred than the other methods. Even if it is too complicated and time consuming, then how we overcome over this problem?
No, I will not recommend it. I will rather recommend that depending on the type of problem, if you really want to do a nonlinear time history analysis, then before that you must be very comfortable with the structural response for static loads and dynamic loads, considering the linear behavior. So first
Yes,
you carry out those analysis, linear static,
yes,
then linear dynamic, and then push over, and after that you venture into the time history analysis. See, it's very easy to do the analysis, no problem with that, but it is extremely difficult to understand the output, if it is
yes,
right or wrong.
yes, sir.
So before that, you have to get the feel of the structure by carrying out simple analysis.
Yes, sir. Okay, sir. Thank you, sir.
Yeah.
Hello.
Sir, I have one more doubt.
Yes, Sarfaraz?
Sir, while we perform equivalent static analysis and then we get the root displacement from it. So in the pushover analysis, we get when we compare it with the equivalent static, then the displacement controlled method if you adopt, then the roof displacement will be our displacement in pushover.
No, no. See, I think you are mixing two different issues here. If I understand your question properly, you want to compare the results of nonlinear pushover analysis
No, no,
with
no, sir.
equivalent, yeah, with equivalent static analysis.
No, sir.
Okay.
Suppose if I have done an analysis of a simple multi-story using equivalent static, and I have found a roof displacement.
Okay.
Suppose I have 100 mm. So will
Okay.
it be my target displacement in the pushover?
Will it be?
It be my target displacement in the
Oh, okay.
pushover.
Okay. Not necessarily. See, in pushover, why do we worry about the target displacement? If you really want to find out how the structure behaves from starting to failure, you plot it completely. If the structure fails at 250 mm, let it fail. After that, you find out at what level of lateral displacement you want the structure to be designed for. Let us say you want to find out the performance point, right? So that you can do. But target displacement is the term generally used by people in those software where it is not possible to degrade the strength. Okay, otherwise you can continue the the pushover analysis till it fails, and then you can say that the 100 mm of displacement that was given by the equivalent static method of analysis, if I consider here in pushover at 100 mm displacement, this is the force. That's all.
So this is basically the force-based method. But if I control the displacement, then I can put that displacement in here only.
You mean to say the equivalent static method is force based?
No, no. Means I want to say that if I don't define the target displacement and only the force will get increasing, then I will get the collapse display. Means
No, no,
get
no.
the final displacement at which the our structure collapse.
No, no. You have not understood it. What I said, you don't limit the displacement, the ultimate displacement in pushover analysis. It will always be the displacement control method. What I'm saying is, you don't ask the software to do the analysis only up to 100 mm.
Okay.
You can increase the displacement levels. The analysis will always be displacement based. You increase it till failure, maybe 500, maybe 300, whatever. And then
Okay, so
you
it is
can
not
say that,
necessary that we have to given the displacement up to that level only. We
no,
can
no,
give it.
yeah,
And
it is not necessary.
okay, thanks, sir.
Okay.
Hello.
Yes, Vaibhav.
Sir, I want to ask if I'm not comparing the results of experimental analysis, for example, if I only want to check the behavior of a column or a beam, which I have done analysis on E-tabs using a fixed strength like M25 or M30. So even in that case, also while analyzing on another software, I have to use higher strength, same strength.
See, if you use all the safety factors and then you compute the material strength, and this material strength you provide to SAP or ETABS as the input, you will get the output. What I'm saying is this output, you cannot say that this is the real output of the structure, but this is the design strength of the structure, right? If you want to compare your results with the design codes, then you can use all those safety factors and then specify the materials. But if you want to know the real capacity of the structure, there is a 4-story building. After an earthquake, that building collapsed. I'm looking at that building and I want to know what was the strength of this building. So if I can get all the section properties, I can collect some materials from site. I come back to the lab, do the testing, and if I do it in pushover, nonlinear pushover analysis, if I do in SAP 2000, how will I match the results? How will I know what was the real capacity of the building? Can I know the real capacity if I model M25? No, I have to model the realistic strength, right? So it depends on what application you are using. If you are comparing results with experimental, you cannot use the reduced strength or you cannot use the design strength. You have to use the realistic strength. If you want to compare, let us say, your design strength, then of course you go ahead with the design strength values of your materials.
Okay, sir. Understood.
Yeah.
Thank you.
So, thank you very much, sir.
Okay. Thank
So
you.
before concluding this short-term training program on Introduction to Seismic Analysis and Design of Structures, I would like to thank all the speakers, Professor Sajal Kanti Dev sir, Professor Kaustubh Das Gupta sir, Professor Sandeep Das sir, and Professor Hemant Kaushik sir for sparing time from their busy schedule and delivering very informative lectures. I would again thank Professor Hemant Kaushik sir for coordinating with the other speakers and convincing them for this program. I would like to thank the faculty members of Civil Engineering Department JEC Jabalpur, and I appreciate Mr. Vivek Vishwakarma for coordinating this program with me. At the end, I would like to thank our head of department, Professor Rajiv Chandak sir, for motivating us to conduct such type of program. Thank you very much for being part of this program. Thank you.
Thank you, everyone. It was nice. Thanks, Vipin, for inviting me here. It was nice, interesting week for me as well, because continuing with 1 week sitting on, on laptop without looking at you. That is why I think first or second lecture I asked you to let the people speak. Otherwise,
Yes,
it
sir.
was really monotonic.
Yeah.
So thanks to all the participants.
Yeah. Thank you, sir, for giving this opportunity. And I hope in future also after this COVID end, we hope that we'll invite you to come to Jabalpur and give us this
Sure.
opportunity and deliver lecture. So
Sure.
thank you very much.
Yeah. Bye bye.
Yeah.